Okay, so let's say, let us go back here. Now we know, say, a simple system like the first one here. If we focus on the degree of freedom, you know, this system has 6 degrees of freedom. Meaning, if you can identify all these 6 in numbers, you can obtain any information that you want from this frame, okay? Whether or not it's the internal axial force, shear force, or bending moment. Just those 3 are the most important thing, okay? So let's say, in the calculation, however, the more or the most dominant internal force is bending moment. So generally, yes, that would be the axial force, which is also important, and the shear force. But let's say some axial force in this member would not be as important, even though that it will exist. Okay, so if we don't really want to know how much stress is going to be here, it means that we can neglect the axial deformation of the structure. By doing that, we can reduce the degree of freedom even further. So let's say I'm going to revisit this one again. To avoid confusion, let me draw it here. So now let's say from this one. Okay, in the beginning, you now know that this one has 1, 2, 3, the horizontal movement, the vertical movement, and the rotation of the joint. So 3 degrees of freedom each. Okay, so there's another joint here. So that means in the beginning, we know that this system has 6 degrees of freedom. So let's say if I say if axial deformation is neglected, that means the axial deformation of the compression or tension members are not important. We can neglect that. So that means I can remove this because the axial deformation of the column will not be important. So I don't need that. It's going to be negligible. It's going to be close to 0 because you think how much your column is going to be shortened by the axial force. It's not important. It's not going to, you know, say interfere much with the most dominating force in the member, which is the moment. So I can neglect this. I can neglect that. Okay, let's erase the whole thing, so to speak. So let's say if the axial deformation is neglected. To clarify this, let me change this color into, say, orange. If axial deformation is neglected, we still have, we still have rotation, right? Because that's nothing to do with axial deformation. The axial deformation of the column will be gone because we don't really care about that. It's going to be close to zero. So you can eliminate 2. So what about this? Horizontal. If we say axial deformation can be neglected, it means that the axial deformation of this member is going to be close to 0, right? Are you with me? So if the axial deformation is neglected, we don't care how much this member is shortened or elongated. So I can say that I can assume these 2 displacement to be the same. Because if the deformation, if the displacement on the left and on the right are equal, it means that this member would stay the same. Its length would stay the same, right? In other words, its axial deformation cannot be neglected. But still, because when you push this frame, it will move to the side. So these horizontal displacements should be the same due to the axial deformation being negligible, but still you cannot erase them both. You need to have one to identify the horizontal movement of your system. Okay, so that means you need to have at least one to tell you how much your structure sways to the side. We call that Sidesway problem. So you can neglect the axial deformation in both columns and the axial deformation in the beam by neglecting one horizontal displacement at this floor level. But you still need to have one because this joint, if it's going to move to the left, it's going to move exactly the same as this joint. So one horizontal displacement will be enough to identify the system. So that means it comes down to 3 degrees of freedom if the axial deformation is neglected. Any question? But you need to have one. Any question? I suppose no. So let's go back to this system and say, okay, this one, you have a lot of system going on now, this picture. When you count the degree of freedom, generally you would be able to count 15, right? So what if I say axial deformation is neglected? How many degrees of freedom are you going to have left for this? Anyone? How many?
10.
10. 10, that would mean 5 rotations. And what about the other 5? Of course, you can neglect this vertical displacement, right? Because now we don't care about the change of the deformation of the column itself. So we can neglect this vertical displacement. 5. What about the other 5 come from? Now, when this frame is going to move to the side, when I say axial deformation is neglected, I don't care about the axial deformation of these 4 members either, right? Meaning I am going to say that they all move at the same amount of displacement, meaning the deflected shape is going to look like this. They will go together. Should be curved, much like a curve. Okay, but they move with the same magnitude. Okay, and the joint, the rigid joint, you know, from structural analysis number 1, you know, the angle must remain the same. It has to be the same. So it means that I only need to know one horizontal displacement of any of them. And the rest will be the same, right? Because I say the axial deformation is neglected or negligible. Okay, so that one, how many we're going to have if axial deformation can be neglected? not 10. We can neglect 5 in the vertical directions, but we're going to need some for the horizontal movement. So how many, folks? No answer this time.
Maybe 11.
More than 10. Thank you for responding anyway. So don't worry if you don't get it right, because at least you think. So when I explain more, you get the picture. We need 5 rotations, correct? Yeah, okay. We need 5 rotations for the rotation of each joint, correct? So that's 5. We don't need the vertical displacement because we don't care about the axial deformation of the column. So 5 is gone. 5 vertical reactions, 5 vertical displacements are gone, out of the question. We don't care about them. So that's down to 10. But we still need to know how much our structure moves to the side, correct? And when they all move together, when I can say that, use different color. When I say, okay, this is delta. This is also delta. That is delta, that is delta, that is delta. That means I need one more to identify the displacement of the structure, correct? So I can't have 5 because that means I will only know the joint rotation. But I need to know how much my system moves to the side as well. And when I say the axial deformation can be neglected, it means that these horizontal members, this one, this one, this one, this one, you know, they will move with the same horizontal displacement. Because if they don't move with the same horizontal displacement, then we have the axial deformation, correct? So all these joints, all these 5 joints, they must move with the equal amount of displacement so that the axial deformation can be neglected, the assumption can hold true. But they move if I push them. So that means in the end, our degree of freedom should come down to how many? 6 degrees of freedom. If axial deformation is neglected. Okay, it's down to 6. 5 rotations and 1 horizontal displacement for this level. Okay, you need to have 1. So now, can you tell me how many of this one? If I neglect the axial deformation of this frame, how many degrees of freedom do I have for this one? Think about it, take your time. Please don't take one day. It should take like a minute or so. Hello. Hello, how many? The rotation will be straightforward, right? It's just the horizontal displacement.
What about 11?
What about 11? How many joints we have, PIs?
10.
10 joints, right? So that's 10 rotation, right?
Yes.
11.
And the 1 horizontal. Oh, 12, right?
Yeah, good. That would be 12 because you now have 2
floor
levels.
Yeah.
So you need to have 1 horizontal displacement for each floor. So very good. In the end, that with 12, you almost got it. You know, it just slip through your finger like that. So here, yes, it's going to be 12 degrees of freedom if axial deformation is neglected. Okay, very important. Okay, so any question, folks? You must be able to identify the degree of freedom of your structure. The failure to identify the degree of freedom is the failure to identify the structure itself. To put it plainly, it's a failure to identify what you need to solve. Okay, so in this class, generally, I would ask you to identify degree of freedom before you do anything. And only a handful of students, they are pretty muddy about this. So if you are muddy about this is, you know, one of the following reasons. First, well, you don't know anything about it. You don't understand it. So you hide your lack of knowledge behind being muddy. Second, you probably know it, but you are an untidy person. You just want to get the calculation going. So you omit this process. You don't want to write about it because you know it doesn't really, you know, help your calculation. If you know what you need to do, you just want to do it. But I suppose things are going to be okay if you calculate everything right to the end. But if you mess it up somewhere, it becomes absolutely impossible for me to track your work because you messed your step. I am not saying that you need to be very thorough, very tidy, and you know everything will be written in perfect order or something like that, because you can say I am a freestyle person myself, but it would help you a great deal if you can organize your work, especially if you are not, say, a very error-free person. Okay, some can focus really well while doing the work, so they can just, you know, carry on everything from the beginning to the end in perfection. But some just get distracted along the way. So, you know, when you solve something and the numbers come out bad, you would know, this doesn't feel right. I need to go back and check stuff like that. So yeah, if you are tidy, if your work is really well organized, you can just go back and revisit the work without any, you know, horrible feelings. But if you are not very well organized yourself, even you don't want to go back to look at your own work, right? You know what I mean? So when you think perhaps you may have made a mistake, when you think perhaps I should, you know, check everything again before I go further, and then you don't want to because you don't want to read your own handwriting. That ever, something like this ever occur to you? It has to me, you know. In the undergrad level, I never read my own own lecture. I did do a lot of lecture myself, but I never read it. I never read my own lecture. It's just like, I don't want to touch it like that. So, and because, you know, I wasn't very happy doing the undergrad work. So, you know, did the lecture to my utmost ability, but for some reason, I didn't really want to read it. And, you know, it's just the same. If you don't organize your work very well, you don't want to go back and take a look at it. Okay. And you will know in time that this analysis, this level is not, say, perhaps not as difficult as the force method in structural analysis, because you will see it will become methodical. It has procedure. It has distinctive steps. If you can follow them, if you focus enough, you should be able to get through this. But then again, it should begin from the identification of the system. If you mess it up from the beginning and say, if I'm in a bad mood, I don't want to follow your work because it's so messed up. And no, some of you just you write as if you were using a magnifying glass. You know what I mean? Why do you want to go so tiny? And because some of you, you know, it's the fashion that you've had before. You remove the support and you replace your support by the unknowns. It becomes even more messy if you get things wrong. So do identify, do try to keep to this, keep your work to the steps for your own sake. Okay, so that means, in a nutshell, the ability to identify the unknowns is of paramount. Okay, it's paramount. Maybe we go back to the rubric description again here. You see, it all begins here with the ability to identify unknowns and make problem statements. Okay, you need to be able to identify them. So before you set up your equation, you fail to identify it very clearly, or you set up your equations not according to your identification of the problems, you know, I have the right not to grade your work further than the first level because everything has been stated very clearly here. Okay. All right. So now let's come back here and this one. Let's go back to the system of the building. So now in the beginning, I tell you why we need to have the more complicated system, because we build tall buildings, and tall buildings, or you know, even not so tall, the factory and the warehouse, they need the lateral load system because the buildings will come under the lateral load. And when we talk about the lateral load system, you either have the frame like we always do in this class. Sometimes if you can put the brace on, you're going to have the brace frame like in the steel design class that you just saw in the day or two ago. And sometimes that lateral load system can be something so large and stiff like the shear wall, but the shear wall is quite an expensive one. We are talking about the wall of concrete. Okay, if you name something the shear wall, it's not a brick wall in your house. A wall in your house is made of brick. That is not a structural system. It's a wall as a partition to create rooms, to create privacy. But the wall in the structure, the structural wall, must be able to withstand the load. And the shear wall is the RC wall, is the reinforced concrete wall. Inside it, it's full of steel reinforcement, so it's a very expensive wall. Okay, so when you have a building like this, let's take a look at this building. Okay, and I'm going to redraw it. Hey, are you still with me so far?
Yes, yes.
Just you?
Yes, sir.
Okay. I have a feeling like you are beginning to feel the pressure of the third year. Am I right? Is that the case? No answer. So I bet that is the case. Yes, this semester is going to be very, very tough. But so far, a lot of students have made it out of this semester. you know, by dropping this class or by not dropping it. Many people have made it out alive, and so shall you. But yes, it's going to be quite tough. But that also means that you need to up your game. You need to stay focused. You need to be able to manage your time very well. You can probably slacken off. You are young and full of energy. So it comes properly in terms of your age. So let's hope that you can handle this. Okay. So now without further ado, let's go back to the building. This is too steep. Say, okay, I have a building like this. Okay. So now let's say this building is going to be hit by window. Okay. So let's say the wind is going to come in this direction. Ooh, it's going to hit your building head on to create a wind pressure. So, you know the situation, and the wind is going to come in. And in fact, the wind can also come in this direction. But let's say, you know, you have to take care of both directions. But for the sake of, you know, demonstration, let us focus on one direction first. So when the wind is going to come in this direction, the wind pressure is going to act on this surface, right? So when I look side view, this side is slightly longer than this side, okay? So when I look at this view, I will see something like this. Correct? With the wind coming in. So when you see a picture like this, you know that you need the system in this direction, right? The system in this direction must be the one that has to withstand this wind. Okay, this orange frame is this one. Okay, and you may have a lot of orange frame in this direction. You may have more here. Or here. And that means if you have a lot of frames, each frame will try to help take this wind load. And so in the same manner as you have had before, the width that each frame will be responsible for, we call it the tributary width, right? It is going to be half the distance between each frame. So that becomes the tributary width. If you decide to have, like, say, in this picture, 5 frames. So, in fact, in the beginning, say this is the pressure coming in, and generally the pressure, the wind pressure comes in terms of force per area. Say, for example, wind pressure comes in terms of load per area. Okay, so when you focus on the frame like this picture, if you focus on one two-dimensional frame. That's what I wanted to say. This load, must be multiplied by the tributary width so that the problem becomes 2D, right? So this one is going to be W, which is come from the pressure multiplied by the tributary width. Right? So if it's a two-dimensional problem, this pressure should be in terms of load per length or W, right? And when I say the frame, I'm going to make it more realistic by perhaps writing more columns in it. So in the real world, looks like that. Okay. Stuff like that. So now it's our job to say how many frames are we going to need to have to withstand the loads. So let's say for this picture in particular, you can have 1, 2, 3, 4, 5 frames. But you can say, I don't need 5, I need 3. I don't need this one and I don't need that one. I can use 3. I can use only this one, that one, and then that one. Right? This is our job to indicate what system we are going to use so that the building has a proper structure to withstand the load. Now, let's take a look at example number 1. You guys have this file already? Hello, you guys have this one?
Yes.
Yes.
Okay, thank you. So let's take a look at this one and see from this one, can we draw the free body diagram of the frames in grid B, okay, with wind load acting on them? Assume a floor height is 3 meters. Is something missing? Okay, that it's 30 meters high, and the frame in grid B, this is grid B, so that's the one. It's a frame in this one. This is the engineering work for real. The main reason that I add this to the class is that funny how architects have a class about something like this, but engineers don't. So you only know how to calculate the stuff, but you're not exposed to how to create a system. Okay, so this should be good enough. So let's look at the frame B. It's a frame in this line. So it's basically this frame. Okay, and then back there. So let's say there is no further information here indicating how many frames you are going to use to withstand the load. Whatever you do, when you select the frame to withstand the horizontal load, you should try to make your system symmetric. All right. So let's say if I ask how many for the frame in the grid B is going to take, let's say it means that we are going to use every frame available. We're going to use this one, we're going to use that one, and we're going to use that one to try to sustain the wind coming in this direction. So if you talk about frame in B, it means that the wind will come in this direction, correct? So now let's take a look at the floor plan. What would be the tributary width for frame in grid B, folks?
Six.
6. Anyone else? Anyone else? Hello? Okay, 6 it is. Yes, that is correct, because when you look at this, the width that the frame in grid B will have to be responsible for is this one, right? Between the frame in grid A and the frame in grid C. So that becomes the width. And if, you know, say 3 at 6 meters each, it means this is 6, this is 6, this is 6. So that is also 6. Okay, that also means the frame in grid A only responsible for the tributary width of 3 meters, right? But grid B is 6, and it's going to be very similar to that one in grid C. Another 6 here, and then another 3 here in the end. So 6 would be the tributary width for the frame in grid B. And now this is what the wind load looks like. So I think sometimes when you change the word into the PDF file, this happens, just got lost. So the total height is 30 meters. And you know what? This is what the wind load in the old days look like. Because the Building Act used to say, if you want to design a building, you can use this wind load on the building. So the first 10 meters is to be equal to this, the next 10, and then the next, and then you keep using this. Things like this. You can start, you know, acclimatizing yourselves with the Building Act and so and so, because this semester you're going to be using that a lot. Okay, so there we have it. But now there is a more complicated and a better method to calculate the wind load. And they give you equations to calculate the wind pressure acting on the building. And the equation will account for so many realistic factors, such as the location of your building, the terrain. You know, if your building is on the open terrain, you know, the wind is going to be different from the building in, say, a metropolitan area like Bangkok. They're going to be different, or the shape of the building, and so and so. Okay, so with this, now you can calculate this, because you know that the tributary width is how much? 6 meters, right? So this is a piece of cake. Now, I wouldn't mind if you don't draw the frame in grid B extremely correctly, because I only care about the load, you know, when I ask this. But if I am going to draw this correctly, how many columns we have? 6, right? 1, 2, 3, 4, 5, and then 6. And the total height is 10 meters. Say I have actually assume floor height of 3 meters. So the 10 meters here will not just coincide with the floor, but anyway, you have like 3 floors and a little bit more, and then so and so. So let's say, forgive me for not drawing everything. Okay, so you just keep drawing this, so and so. But what is more important is that you must know that, okay, now the load here, say it's gonna be more like that. The load here now, because I say that for grid B, right? So here, it is going to be equal to 1200 multiplied by the tributary width of 6 meters. So in the end, that is 7,200 Newton per meter. That's what I want. That's what I want you to know. That's what I want you to be able to do. Okay? So the next one, this will be, can you tell me how much? $800, right? Multiply by the tributary width would remain the same, right? 6. So this is 4,800 Newton per meter. And say, last one.
I have it.
Sorry? Oh yeah, 500. Thank you. Thanks a lot. It's 500 multiplied by the same tributary width. That is 6. That is 3,000, right? Wow, takes a while. So you know, that's the basic idea of calculating the wind load acting on your building for a typical structure like this, like a box like this. Okay, so now let's say I want to focus on the wind in this direction now. If the wind comes in this direction, now you can have how many frames in here? You can have 1, 2, 3, 4, 5, and 6. Now let's imagine yourself as an engineer. Say how many frames you want to use. Huh? No response.
What about 4?
4? Okay, pick them for me.
In the middle, or 1, 2.
Okay, let's call them. Let's have a roll call because we have 1, 2, 3, 4, 5, 6. Which in which frame do you want to use?
2 to 5.
2 to 5. I say that's not a bad choice, but can I rectify something? Because if you want to use 2 to 5, realistically, you don't have anything on 1 and 6, correct?
Yes.
So when it's going to be slightly difficult to try to say handle the wind load in this zone, right? But you know, I love your choice because it needs more explanation. How are you going to transfer the wind in this purple patch, pun intended, to the frame on grid number 2? Difficult, right?
Yes, yes.
But it's possible. It's possible to do that. Let's say we're going to do that. Let's say we can. Okay? Let's say we can. So that means this purple region area will have to be taken care of by frame number 2 alone. Correct? And,
Yes.
and frame number 2 will also have to take care of the area between frame number 2 and number 3. So this becomes the tributary area for frame number 2, right? Am I correct?
Yes.
Okay, so far so good. And this will be the tributary area for frame number 3. Half between 4 and then the rest of the half between 2 and itself. Right? So in this case, now we can say if we focus on number 3, here, if say in another direction, so that's my direction. Okay, if frames in 2 through 5 are used, now for frame in grid number 3, let us go ahead and calculate the window. Okay, let's skip the drawing part. Now I wouldn't mind, you can draw this, you cannot draw this properly, but anyway, try to be professional, okay? Now you're going to have, say, 3 wind load again. Okay, so here we are. So this one is going to be equal to 1200, am I right? Yeah, 1200 multiplied by the tributary width, which is now this one, which is 8 meters, right? Multiplied by 8. And that gives you 9,600, right? Newton per meter. And then this one becomes 1200. Oops, that's wrong. 800. Multiplied by 8. How much is that? 64, right?
Yes.
Newton per meter. And that would be 500 multiplied by 8. That's 4,000. Okay, not difficult. Not difficult at all. Is there any question? Is there any question? Let's stop the record.